Welcome to our video on hack CPU implementation. The diagram is a simulation of hack computer chip with three main components: instruction memory, CPU, and data memory. In a hack computer, the CPU is responsible for executing instruction in the instruction memory. These instructions are typically written in an assembly language or machine code, which the CPU can understand and execute. The CPU takes instruction, a reset signal, and input from the instruction memory as input, and uses its internal circuit to decode and execute the instruction. In short, the instruction memory stores the instruction for a program. The PC, which stands for program counter, is a register that holds the address of the next instruction to be executed by the CPU. In a hacked computer, the data memory is used to store data that the CPU uses during its operation. The data memory is typically implemented using a memory technology. Data memory can be read from and written to by the CPU, typically through memory mapped IO operation. Moving on to the next slide, we have the CPU interface. From where we can see we have three inputs. The one which provide data to the CPU for processing, the other specify the operation to be performed by the CPU, and the next one is to reset the CPU to its initial state. We also have four outcomes of it. First, we have out M, which refers for data memory, and the second one, memory write operation. The third is likely to be for memory address operation. And the fourth one is PC, again, which stands for program counter, refers to a program counter output port. These output ports are used by the CPU to communicate with other components in the computer system, such as memory and peripheral devices. Moving on to the next slide, we have hack CPU architecture. So, here we have a description of computer hardware in the loop integration platform CPU, which is basically a digital circuit that can execute instruction to perform various operations. The CPU consists of several components, including input and output register, multiplexer, and functional unit, such as the arithmetic logical unit, PC, which stands for program counter, and register for storing data. The input register in instruction and reset receive input data, and the output register out M, write M, address M, and PC provide output data. The instruction register receives a 16-bit instruction that specify the operation to be performed by the CPU. The reset input is used to reset the program counter to its initial value. The instruction is passed through a series of multiplexer and logical gates to control the flow of data and control signal throughout the CPU. Over here, we discuss about 16-bit instruction. So let me tell you before going ahead, we have two kind of instruction. First one is the A instruction, which is represented by the syntax at the rate value. It sets the value of A register to a non-negative decimal constant or a symbol referring to such a constant. Then we have C instruction, which has semantics of compute desk jump. So compute refers to the computation to be performed, there stores the result in the destination, and jump into an instruction based on the computation. So now all this we have basically we were supposed to explain the CPU HDL code, which is given in the task sheet. So the first page we have the code which appears to be defining a complex hardware instruction processor CPU with several input and output signal. Over here, the input in M is a signal that represents 16-bit memory data. Instruction is an input signal that represents a 16-bit instruction to be executed by the CPU. Reset is an input signal that, when active, resets the CPU to its initial state. Moving out to the output signals, we have out M, which represents 16-bit memory data. Write M, which is an output signal that, when active, indicates that the CPU is currently writing to memory. And the address M15 is an output signal that represents the 15-bit memory address being accessed by the CPU. We have PC15, which is an output signal again that represents the 15-bit program counter value of the CPU. Now, moving on to the second page, we have a code which appears to be defining a few logic gates and components that are used to control the behavior of the CPU's arithmetic logic unit and register. The CPU, first of all, to go further, we have to understand that the CPU decodes 16-bit instruction into an opcode and a 15-bit value. So, if the opcode is 0, the instruction is an A instruction, and the CPU stores a specified 15-bit value in the A register. If the opcode is 1, the instruction is a C instruction, and the CPU performs the computation in the ALU with the output being stored in the A register. Now, a multiplexer is used to determine whether the instruction or the ALU output is stored in the A register. An AND gate is used to determine if the instruction is a C instruction. The multiplexer selects which value, either the value from A instruction or the output from the ALU, should be stored in the A register. Now, so in the code, we can see like the instruction is first passed through a NOT gate, which inverts its 50th bit and then passed through another NOT gate to invert the output of the first NOT gate. The CLNS output is used as a control bit signal for several components in the CPU. Now, moving on to the next part of the code. Okay, so there is an OR gate that controls the load bit for the A register. The A register stores the value that is fed into it from multiplexer and the OR gate output. Another multiplexer known as the MUX16 selects between the output of the A register and the value currently stored in the data memory register. This will select which one to output, either A or M, and feeds into the ALU depending on 12-bit instruction value. So the AND gate is used to determine if the ALU output should be loaded into the D register. The ALU performs a function on the value stored in the D register and the A or M register and generates an output. The ALU also has an input control bit such as the ZX, ZY, NX, NY, F, NO, which indicate which function to perform on the input, and output control bits such as ZR and NG, which determine the property of the result. The next part of the code includes two OR gate and an AND gate that sets the ALU output in order to write to the data memory. So the first OR gate code line determines the address of the write operation, and the second one determines the content of the data memory. And the AND gate output is a value that allows the content to be written to the data memory. So furthermore, we go to the program counter, which is also known as PC, which is a register that contains the address of the instruction to be fetched. The load bit of the PC is determined by the jump bits and the ALU outputs. This line of code determines the jump condition and checks the output to see if the condition are met. If the instruction is a C instruction and the conditions are met, the program counter is loaded with a value that will cause the CPU to jump to the specified value or the symbol. If the PC is not loaded, then it is incremented, which means the CPU will read the next instruction. So this is